Welcome to another glorious day of physical science. Today we're going to be talking about behavior of waves. So let's dig into it right away. So first thing we're going to start talking about is something called reflection. Now reflection is when a wave strikes an object and bounces off it. Now all types of waves will reflect, whether it be sound waves, whether it be light waves, whether it be electromagnetic waves like radio waves. An echo is a result of reflecting sound waves. So as you can see here, you have a person talking, and as the sound is going in that direction, wrong way, you'll notice that it hits the wall and then bounces back. As it bounces back, it comes back to that person's ears. Now bats, dolphins, and other animals will use echoes, something called echolocation, to find their prey or be able to move around. It sends out a pulse of ultrasound and measures the time needed for the sound of travel to a school of fish and back to the boat. If a school is 16 meters below the surface, how long would it take sound to make the round trip in the water? The velocity of sound in water is 1,484 meters per second. So here we know that the distance is 16 meters, but remember, the pulse is going from the boat down to the fish and then back up to the boat. So it's going to be 16 meters times 2. The velocity was given as 1,484. We're trying to solve for time. So our mother equation is V equals D divided by T. We're going to change that because we're solving for T. Is T equals D divided by V. We plug in our numbers, and we get an answer of 0.022 seconds. Now, fish finders, of course, there's many different types, and depending upon the amount you want to spend, you're going to get different types of images. Here are a couple of examples here, ranging from a black and white to something a lot more detailed. Next, I want to talk about something called a normal. Now, the normal it's an imaginary line, right? You don't actually see it. It's a pretend line, imaginary line that is perpendicular, right, 90 degrees to the surface of the mirror or reflective surface. So we take a look at the law of reflection. It says that the law of reflection, the angle of incidence is equal to the angle of reflection, right? So basically, if we were going to come down and simplify it to the most simplest terms, it simply means that the law of reflection says that the angle in is going to equal the angle coming out of the reflective surface. Now, we look at the diagram here. Here we have our mirror. The normal is right here, which is our right here. Oops. That's our normal right there. That normal is not physically seen. It's 90 degrees perpendicular to the surface of the mirror here. Oops. Now, looking at the angle coming in, here we have, this is known as the incident ray. The ray coming into the mirror. When it reflects off the mirror, this is known as the reflected ray, or the ray of reflection. The angle of incidence is the angle between the incident ray and the normal. All right, the incident ray here and the normal. Now, the angle of reflection is the angle from the normal to the reflected ray. We represent the angle of incidence by a lowercase I and the angle of reflection with a lowercase r. The angle of incidence and the angle of reflection are equal to one another. Remember, angle in equals angle out. Refraction is simply the bending of the wave caused by a change in speed as it travels from one medium to another. Here we have an example of paintbrush in a glass of water. As you can see here, when we look at where the paintbrush is in the air versus the water, it looks like the paintbrush actually breaks or bends here, which is, of course, not actually the case. And that's because of the bending of light. Now, depending upon the direction that the light is traveling, will determine a couple of things. It'll ask if the light's going from a dense to a less dense material, like from water to air. Then what's going to happen is going from a more dense to a less dense will cause the beam to speed up. And as the beam speeds up, it'll bend away from the normal. On the other hand, if the beam is going from a less dense, like air, to a more dense, like water, then the wave will slow down and it will bend towards the normal. So here we have the normal, right? The light comes in, and it would normally, if it was traveling straight, it would normally go like so. Well, a little more straighter than I did, but because it slows, it bends down closer towards the normal. Here we have, what is this used for? Well, if you're on a desert island and you need to fish, if you're going to try to spear or harpoon a fish, you got to make sure where you're hitting. You got to make sure that the real position actually is lower than what it actually is because of that refraction. Next, I want to talk about something called diffraction. Diffraction is the bending of waves around corners. Now, whether this be, for example, you can see on the left hand here a picture of the sunset. Well, there's no sun in the sky, but you'll also notice that it's light out, or it's starting to become light out. Why? Because the light from the sun is bending around the surface of the earth, and you start to have some light, whether it be sunset or sunrise. Right? If you are middle picture with sound bends around the corner here. If this person is on the corner, it's not in direct line of the boombox, but you can still hear the sound of that music being played from that boombox. And then, of course, at nighttime, when you take a look at a light in the hallway, you have a very dark area, right? But you'll notice here that the light, as it comes through here, it's bending, right? You can actually kind of see how it kind of bends from the corner here all the way out through the light here. Another thing that can happen with waves is that they can interfere with one another. Interference simply is the process of two or more waves overlapping and combining to form a new wave. There's two different types of interference that we're going to talk about. The first type of interference that we're going to talk about is called constructive or additive interference. When this happens is waves get added together. So here we have wave A and wave B. They're traveling in opposite directions. As they come together, once they are in the same spot, what happens is the wave actually here, you can see here, the wave actually gets bigger. And then the waves continue through and go back to their original size. This is called, remember, constructive interference. Then you have something called destructive or subtractive interference. This is when the waves subtract from each other. Here we have two different waves here, and you can see here that the waves are in actually opposite, where you've got the low part, or the trough of one wave, and the crest of another are in the same spot. What ends up happening is they will subtract each other out. And because it's at the very lowest point and at the very highest point here of these two waves, and if you count up here, they're the same height, they cancel out. All right. Now, a lot of technology here. You take a look at headphones, sound canceling headphones, or noise canceling headphones, or some of the fancy cars actually will sound a lot quieter than some of your cheaper cars because they actually have a device that produces a wave that's opposite of what's being heard in the car. Therefore, it cancels that noise out and it makes it quieter. Standing waves are a special type of wave pattern that forms when waves equal in length, how long they are, and amplitude, how tall they are, but traveling in opposite directions continuously interfere with each other. When this happens, you're going to get something called a node. A node is a location where the waves are interfering and they cancel each other out. This is an example of a standing wave. The node is the area where they're canceling each other out. And then here we have an antinode. This is where the waves get added together, or constructive interference. Then we're going to talk about something called resonance. Now, resonance is the process by which an object is made to vibrate by absorbing energy at its natural frequency. So all matter has a natural frequency. And if you can produce a wave of energy and it strikes another object with that wave's natural frequency, that object will start to vibrate. So here we have a tuning fork here, two tuning forks. Exact same type of tuning fork. We strike tuning fork A. As it vibrates, all right, it sends out those waves out into the room, and those waves strike tuning fork B, which is the exact same tuning fork. What happens is because the tuning fork of A and B have the same natural frequency, tuning fork B starts to vibrate even though it was never touched by or struck. Examples of resonance can be seen here. Here we have on the right-hand side, if you play a guitar, resonance is used in playing guitars or like violins and stuff. You have the shattering of a glass. You can shatter glass if you put enough energy into it and it begins to vibrate. You can shatter a glass, whether with your voice or whatnot. And then you have the other one here is up on top, the Tacoma Bridge. You can see this bridge. There's a little twist right here. That's not normal. And that's because of resonance. It was a fairly strong wind, but because it happened to be the natural frequency of the material here, the bridge started to vibrate back and forth. That's it. Hope you understand. Click on the link, and that's it. Click on the link to view the actual slideshow, to have access to the other links for more information about the different topics.